Okay, so I'll also repeat. So the idea of the chain rule is to find the derivative of composite function. And okay, for example, if we have f of x equals to x squared plus 1 to the power 10, or gx equals to sine 5x, then we want to find its derivative without doing many complicated things. The idea is to write the function as the composite function, or as a composition of two functions. For example, f of x equals to x squared plus 1 to the power 10 is written as the composition of x squared plus 1 and x to the power 10. Okay, and the same applies for sine 5x. We will write it as the composition of 5x and sine x. And the rules for finding the derivative of composite function is that, for example, the derivative of f circle g here is f prime evaluate at gx multiplied by g prime of x. The idea is to first calculate f prime first, calculate it at gx, and then multiply it by g prime calculated at x. Okay, and if we use the Leibniz notation, let's say y is a function of x, y is a function of u, and u is a function of x, then dy dx can be written as dy du multiplied by du dx. And for example, the derivative of x squared plus 1 to the power 10 here, let us say u equals to x squared plus 1 and y equals to u to the power 10, then dy dx, or the derivative of x squared plus 1 to the power 10, is just the product of dy du and du dx. And in this case, dy du is 10 multiplied by u to the power 9, and du dx is 2x. So if we calculate it, then we have 20x x squared plus 1 to the power 9. Okay, okay, so the next example will be, the next example is the derivative of sine 5x. Example 2. So let us calculate the derivative of sine 5x. Okay, so what is the derivative of sine 5x? The same as before, we will write it first as the composite function, so the composition of the function. And more precisely, we have the first function is 5x, and the second function is sine x. So let us write u equals to 5x and y as sine u here. Okay, so you'll see that we start from the inside here, 5x, and then we have sine 5x, so we'll write it as sine u. Okay, we write y as a sine u, where u equals to 5x. Then by the chain rule, dy dx, okay, equals to dy du multiplied by du dx. And in this case, dy du here, because y equals to sine u, so dy du equals to cosine of u. Okay, and then du dx here is 5, because it's just the derivative of 5x. So we'll have 5 cosine of u, and u is 5x. So y dy dx equals to 5 cosine 5x. Okay? So that's the answer. So that's the idea for the chain rule here. And actually, we can repeat the chain rule. For example, the function is written as the composition of 3 functions, let's say 4 functions. We can still repeat the chain rule as well. Okay. So for another example, so let us take a look at the example here. So another example of the chain rule. Let us take a look at the formula for, let's say, ddx of 1 over, let's say, cosine x squared plus 1, for example. Okay. What is the derivative of this one? Okay, you'll see that here, of course, you may use the quotient rule to obtain the derivative of this function, but we may also consider the derivative of 1 over x and using the chain rule. Okay, so in this case, okay, the idea is that okay, so what is the key idea? Okay, so let us write y equals to 1 over cosine, probably I will use another. So y is the 1 over cosine x squared plus 1. Okay. Okay, so first we need to write here this function as the composite function of three functions. Yeah, the composition of three functions. And in this case, we start from the inner function. The inner one, we have u equals to x squared plus 1. Okay, so let u equals to x squared plus 1. And then I can write v as cosine u in this case. Then what is the relation between okay, forget to add x squared plus 1 and v equals to cosine of u. So we can write then y is simply just 1 over v, right? Okay, and in this case, okay, here v is a function of u, namely v equals to cosine of u, and u itself is a function of x, namely u equals to x squared plus 1. So we have dy dx equals to, okay, here is the variable is a v, dy dv, multiplied by dv du, and then multiply once again by du dx. Okay, so in this case, dy dx equals to dy dv, and then multiply once again by dv dx. Sorry, dv du, and then multiply once again by du dx. Okay, so in this case, since y equals to 1 over v, then the derivative of y with respect to v is minus 1 multiplied by v to the power minus 2. And then dv du, v equals to cosine of u, so dv du equals to minus sine u. And then du dx, u equals to x squared plus 1, so du dx equals to 2x. Okay, okay, of course we can combine this. Okay, so I have 1 over v squared, v equals to cosine, okay, cosine square of u, okay, multiplied by sorry, the minus sign will cancel. So I have 1 over cosine square of u. Sine u equals to sine x squared plus 1, right? Multiplied by 2x. And of course, you can replace u here directly by x squared plus 1. So in the end, we will have, after simplifying this one, we'll have 2x sine x squared plus 1 divided by cosine square x squared plus 1. Okay. Cosine x squared plus 1. Okay, so that's the derivative here. Okay, any question or comment up to this point? Yes. Previous slide. Yes. Yeah. Pardon. The question is yes. So 1 over v is v to the power minus 1. Yeah, of course. Yeah. You mean this step? This one? The previous one? The question is yes, of course. Okay, yeah, of course you can write it as v to the power minus 1. This is the this one, yes. And then yeah, of course, but I think that we should explain this one. The derivative of x to the power minus 1 is minus 1 multiplied by x to the power minus 2. We cannot omit this step. Okay. That's answer your question? Yes? Okay. Any other question or comment? Yeah, of course, sometimes we need to, for example, quickly calculate the chain rule, okay, without writing the appropriate appropriate assumption here. For example, if you want to evaluate the derivative, let's say tangent of 10x here, it's just simply the derivative of tangent is secant square, secant square of 10x, and then multiplied by the derivative of 10x, simply multiplied by 10. Okay, so you get 10 secant square of 10x. But okay, this is quite simple. But if you have quite long expression, it's better to write what is u, what is y, and then write it as dy du multiplied by du dx. Okay, but if the expression is not that complicated, something like this, just a composite function of two simple functions, let's say tangent of 10x, just simply what is the derivative of tangent x? It's the secant square of x. Replace x by 10x, sorry, and then multiply it by the derivative of 10x is 10. Okay, that's the simply the way to write or to solve the derivative by the chain rule. Okay, any question or comment so far about the chain rule? All right. If okay, so if there is no question, so let us continue. So suppose that okay, so I have the following example. So let us solve this one by one. Okay. Suppose that we want to know what is the derivative of square root of 1 minus x squared. Okay. What is the derivative? Okay. So what is the first step? Square root of 1 minus x squared. What is the function u here? That u equals to 1 minus x squared and y equals to square root of u. Okay, right? Then the next step will be to write dy dx as dy dx, write it as dy du dy du multiplied by du dx, right? And what is dy du? So what is the derivative of square root of x, square root of u? Half 1 over square root of u, right? And then what is du dx in this case? Du dx is minus 2x because it's a derivative of 1 minus x squared is minus 2x. So if we simplify this, we will obtain here is the dy dx is minus x over square root of 1 minus x squared. Okay. Square root of 1 minus x. Okay. So that's how we use the chain rule. Okay. Okay. All right. So by using this similar argument, what is the derivative of minus? Okay, of course we can just multiply it by minus 1. The derivative of minus square root of 1 minus x squared here equals to simply x over square root of 1 minus x squared, right? Just multiply it by minus 1. Okay, actually this example has a meaning. The meaning is as follows. Actually, we will continue to the implicit differentiation by using this example. So the idea is that suppose that you want to look for the gradient of the tangent line to the curve to the unit circle. Okay, so we have the curve x squared plus y squared equals to 1, and then we want to find the gradient of the tangent line. Okay, we want to find the gradient of the tangent line at this point. Okay, or at this point, or at this point, this point. Okay, so at any point of this circle except at these 2 points. Okay, at this 2 points, you will see that here there is a singularity here. Okay, at these 2 points, there is no tangent line. Okay, okay, so okay, so the idea is that if we want to find the gradient of the tangent line, then we want to find its derivative, right? The derivative of the function here. And actually, if we have x squared plus y squared equals to 1 here, actually this is the curve here is the combination of 2 graph of the function. Okay, for example, the first one is this upper part here is the graph of y equals to square root of 1 minus x squared. Okay, and the lower part here, let's see, this one is y equals to minus square root of 1 minus x squared. And in the beginning here, we already considered the derivative of this. The derivative of here, the upper part, dy dx here, is the derivative of square root of 1 minus x squared, and we will obtain the result is minus x over square root of 1 minus x squared. And actually we can simplify it by realizing that here y equals to square root of 1 minus x squared, and in this case we have minus x over y. Okay. On the other hand, if y is this function, so dy dx equals to x over square root of 1 minus x squared. And since y equals to minus square root of 1 minus x squared, we always get this one is minus x over y as well. Okay. So of course, this formula holds for any point except these two forbidden point, namely 1, 0 and minus 1, 0, because at this point, the derivative does not exist. So at this point, there is no tangent line there. Okay. So except these 2 points, then the derivative, the gradient of the tangent line to the curve, to the unit circle here is can be calculated by minus x over y. Okay. Okay. So the question is the this separating case here is necessary or not? Should we write y as a square root of 1 minus x squared for the lower part, the upper part, and y equals to minus square root of 1 minus x squared for the lower part, and then calculate the derivative 1 by 1? Or can we calculate the derivative by a more unified approach? That's the question. So that's the motivating example of implicit differentiation. Okay. So to implicit differentiation, here we want to calculate the derivative. Okay. For the purpose, for example, for calculating the gradient of the tangent line to some curve, and the curve is given in a certain equation, and the equation or the curve is not only the graph of the function. Okay, actually here the unit circle here is the combination of the graph of 2 functions, the first function and the second function. But we want to unify this calculation, and okay, sometimes even, okay, I will save. Sometimes the this approach, this case by case approach does not work. For example, if I want to consider the volume of Descartes with the equation, let's say x cubed plus y cubed minus xy equals to 1, for example, the volume of Descartes here actually is quite difficult, maybe impossible, to write y as a function of x here. Okay? It's quite difficult to obtain the formula y as a function of x. Okay, so this is the volume of Descartes. Okay, so suppose that we want to find the tangent line, the gradient of the tangent line at 1, 1. Okay, that's the idea. Okay, but we cannot write y as a function of x. Okay? But we cannot write y as a function of x. Okay, so that's the problem. Okay, so now let us first at this moment, okay, hold this problem, and then we go back to the previous problem for finding the gradient of the tangent line to the unit circle. Okay, so let us go back to the gradient of the unit circle. Okay, so I will write this topic as implicit differentiation. Okay, so for the implicit differentiation here, okay, we'll have x squared plus y squared equals to 1 there. Okay, and we want to verify that dy dx equals to, previously we have minus x over y, and then we want to verify this. So the idea is that to write the terms on the left hand side as the function of x and y, right? Fx comma y as x squared plus y squared, and assume that y is a function of x, then calculate the derivative of fxy with respect to variable x and using the chain rule. Okay, so that's the general idea. Okay, using the chain rule. So that's the general idea. So okay, so we have x squared plus y squared equals to 1 here. And we take its derivative. So the derivative of x squared plus y squared, calculate it. And the derivative of the constant function 1 here. Okay. Of course, the derivative of x squared plus y squared is as follows. So the derivative of x squared is 2x. And then what is the derivative of y squared? Is 2y. But be careful, y is a function of x. So we have to multiply it once again by dy dx. Okay. On the right hand side, we have the derivative of constant function. So the derivative of 1 is 0. Okay. And then we may write 2y dy dx equals to minus 2x. And the conclusion here, just divided by 2y, we get dy dx equals to minus 2x over 2y, or minus x over y. Okay. So you'll see that here we do not need to write y as a function of x, but we can obtain dy dx here. So that's the idea is just write. Okay, we do not need to write y as the square root of 1 minus x squared or minus square root of 1 minus x squared, but we still obtain the dy dx, the derivative of y. Okay, so the idea is, if we have the equation here, just derive the term on the left hand side and on the right hand side of the equation as the derivative of x. Okay, but we have to be careful that y is always a function of x. Okay. So the derivative of x here is 2x. The derivative of y squared is 2y, but do not forget we have to multiply it by dy dx. Okay, and on the right hand side we have this one equals to 0. Okay, and we obtain that the dy dx equals to minus x over y. Okay, so the idea of implicit differentiation is that we do not know the formula of y as a function of x, but we still obtain the derivative of y as a function of x. That's the idea. We do not need to care about the formula of y equals to something x, but still the goal is to find dy dx. And to do that, simply just consider the equation and then take the derivative of the left hand side, take the derivative of the right hand side, and they are equal. And then usually the derivative of the left hand side is complicated, involving x and y. The derivative of the right hand side usually is simple, even usually it's a 0 or a constant. But be careful, the derivative of the left hand side involves the chain rule. Usually do not forget the dy dx. Okay, any question or comment up to this point? All right, if there is no question or comment, let us go back to the previous example about the volume of the card here, x cubed plus y cubed minus xy equals to 1. Okay, and in this case we cannot obtain the formula of y as a function of x easily because it's a cubic equation. It's almost impossible. And still we want to find dy dx, but now at the point 1, 1 here. Okay, let's say at the point 1, 1. Okay, so let us okay, so the question is, what is dy dx? If we evaluate it at x equals to 1 and y equals to 1. So that's the question. Okay, at this point, what is the gradient, and then what is the equation of the tangent line at that point? Okay. Okay, so let us calculate it. So I will move to the whiteboard, and then, oops, where is the whiteboard? And then type the formula of the equation of volume of Descartes. Volume of Descartes. Here I have x cubed plus y cubed minus xy equals to 1. Okay. Okay, so we do not need to write y as a function of x here. Okay, so the idea is that just simply take the derivative. Okay, take the derivative here. So derivative of x cubed plus y cubed minus xy, and this one equals to the derivative of the constant function. Of course, the right hand side is 0, right? Because it's derivative of 1. But we have to take a look at the derivative of the left hand side. The derivative of left hand side, what is the derivative of x cubed? 3x squared. And then what is the derivative of y cubed? 3y squared. But we have to multiply it by dy dx. Okay. Okay, and then the next term, this is a product of two functions. The first function is x, the second function is y. So what is the derivative of xy? Negative y minus x dy dx. Okay. So we just use the derivative of the product of two functions. The first function is x, the second function is y. Okay. The derivative of x is 1, so 1 minus plus 1 multiplied by y plus x multiplied by the derivative of y goes to 0. Okay. Okay, so the next step, just move to the right hand side, have any terms with without dy dx here. So here I can simplify 3y squared dy dx minus where is the minus x dy dx equals to, okay, y minus 3x squared. Okay, and then from this we have dy dx equals to y minus 3x squared divided by 3y squared minus x. And in particular, if I want to calculate dy dx at x equals to 1 and y equals to 1, just simply substitute x equals to 1 and y equals to 1 there. So 1 minus 3, 3 minus 1. That will be minus 1. So here you see that start from the complicated equation here, x cubed plus y cubed minus xy equals to 1. We still can obtain the formula for dy dx here. And in this case, dy dx here is this one. And in particular, for x equals to 1 and y equals to 1, then we get dy dx equals to minus 1. So the interpretation of this calculation is that if we go back to this one, so the gradient of the tangent line here, the gradient of the tangent line to the curve here equals to minus 1. Okay, and if the gradient is minus 1, so of course we have the gradient of the tangent line, and then we have the tangent point, and the tangent point is 1, 1. So just simply calculate it as 1 minus y minus 1 multiply equals to minus 1 multiplied by x minus 1, and simply we have minus x plus 2. So in fact, the equation here, if I draw the equation y equals to minus x plus 2, then it's the tangent tangent line. Okay, the green line, the equation of the green line is y equals to minus x plus 2. Okay, so the idea of implicit differentiation is quite simple. with just without writing y as a function of x, we still, if we have the relationship between y and x, then just simply treat y as a function of x, then take the derivative of the left-hand side of the equation and the right-hand side of the equation with respect to x, and then applying the chain rule, simplifying, and then we get dy dx. Okay, once we get dy dx, then we can calculate it at any point once the formula for dy dx is well defined. Okay. Okay. Any question or comments so far? Okay. If is it clear? Okay. Okay. Now we want to see the application for the implicit differentiation for finding the derivative of the x to the power rational number. Okay. Okay. So let us recall that if I have y equals to x to the power n, where n equals to 1 is where n is a positive integer, 1, 2, 3, 4, and so forth, then the formula for the derivative is n x to the power n minus 1, right? And of course, this formula also true when I replace n here by a negative 1, minus 1, minus 2, minus 3, minus 4, and so forth. The formula is still the same. Dy dx is just n x to the power n minus 1. Now the question is, what happened if I replace n here by any rational number? For example, I replace it by 13 over 11, 13 over 7, or 101 over 99, for example. The question is, how do we calculate the derivative? Okay, so if I have y equals to x to the power r, where r is a rational number, then the question is, what is dy dx? Of course, we can hope, or our hope is to have the similar formula, namely r x to the power r minus 1. Okay? Of course, omitting the case where x to the power r minus 1 is undefined. Okay? So, yeah, actually, we have the formula here, y equals to x to the power r, but we do not know the derivative here. So the idea is, okay, starting from the explicit formula, we change it into implicit formula. Okay, so let us write r equals to p over q, where p and q are integers, namely the positive one or the negative one. Of course, omitting the case where q is non-zero, right? So since r is a rational number, we always write it as r equals to ratio of two integers. Let's say these two integers are p and q. Write it as follows. Then, okay, we use this fact here. The only rule for finding the derivative of the power here only applies for the integers. That's why if I write it, okay, so y equals to x to the power r here equals to x to the power p over q, then this is equivalent, okay, since we want to have the derivative of the x to the power something of the integer, then just take the power of q here. So of course, this equivalent with y equals y to the power q equals to x to the power p here. Okay. So now we do not have the explicit formula, namely y equals to some function of x. It's actually given here, but we want to write it in this way because we want to have x to the power integer or y to the power some integer. Okay, so that's the idea. And then if we use the implicit differentiation, then simply just take a look at the derivative of y to the power q and the derivative of x to the power p. Okay, so what is the derivative of y to the power q? We know that p and q are integers, so we can apply this rule, right? Okay, we can apply this formula. Okay, so that's why we can obtain q y to the power q minus 1 and then multiply by, do not forget always, by dy dx. On the other hand, the right hand side will be p x to the power p minus 1. That's it. And then we obtain dy dx equals to p over q x to the power p minus 1 divided by y to the power q minus 1. Okay. And since we want to have the formula for dy dx as the function of x only, then we have to substitute y equals to x to the power p over q there. So dy dx equals to p over q x to the power p minus 1, y to the power q minus 1 is x to the power p over q to the power q minus 1. Okay, and if we can simplify this, p over q x to the power p minus 1 x to the power where is it? P minus p over q, and I can simplify it as p over q x to the power p over q minus 1. And then we know that p over q is, in the beginning, we know that p over q equals to r. So we have r x to the power r minus 1. Okay. So start with y equals to x to the power r, where r is a rational number. So the answer is dy dx till r x to the power r minus 1. Of course, we have to assume that x to the power r minus 1 is defined there. For example, if you have r equals to 1/3, for example, you cannot calculate it at x equals to 0. Okay. All right, so you'll see that although we have the explicit formula, but the implicit differentiation can help us to obtain dy dx by writing as the implicit one, and then applying the derivative and the chain rule as well. Then we get the dy dx for the x to the power r, where r is a rational number. Okay. Any question or comment? Oh, yes. So you see that implicit differentiation is very useful in this case, because we can just simply obtain the dy dx, okay, for out of nowhere. For example, you start with y equals to x to the power a rational number. You do not know how to calculate the derivative. Then write it as an implicit form, because the implicit form here is just the derivative of the power function, but the power here is integer. The power, each power here is integer, and you know the derivative of the y to the power integer or x to the power integer, and then just simply applying the chain rule, okay, simple chain rule, then you get the formula. Okay, okay, any question or comment so far? Is it all right? Okay, if there is no question or comment, I will save this. And then okay, I will post. Okay, so we'll continue to the topic about the higher order derivatives. Okay, the idea for the higher order derivatives is as follows. So let us first recall the definition of the derivative here. So recall that f prime of x equals to the limit as h tends to 0 of fx plus h minus f of x, and then divided by h. So once the limit, this limit exists, then we always obtain the value of the function, the value of the derivative at that point. Okay, and simply this limit defines the derivative function here. So f prime of x is always limit h tends to 0 of fx plus h minus fx divided by h. And the second derivative is simply just the derivative of the first derivative. Okay. Okay, so dd x of f prime of x. And okay, of course, we can write this as, so the second derivative is just by the definition, just the limit as h tends to 0 of f prime evaluated at x plus h minus f prime of x divided by h. So just simply change the role of the function itself, f, by the derivative f prime. Then we obtain the second derivative. And simply, the third derivative, f triple prime of x, is just the derivative of the second derivative. Okay? Derivative of second derivative. And then we may continue this way. The fourth derivative is just the derivative of the third derivative. And then we may define the n derivative, okay, as the following symbol. N f to the power bracket, round bracket n here is the nth derivative. For example, if we consider the polynomial function, let's say if we consider as an example f of x equals to, let's say, x to the power 5 minus 4x square, let's say, plus 2x plus 1, say something like this. Then the first derivative will be f prime of x is 5x to the power 4 minus 8x plus 2, because the derivative of 1 is 0. And then the second derivative, just simply take the derivative of the following function. Then we'll have 5 times 4, 20, x cubed minus 8, for example. And then the third derivative, just the derivative of this one, is 60 x squared, but the derivative of minus 8 is 0. We have 60 x squared. And then the fourth derivative, okay, just simply 120x. And then the fifth derivative here is 120. And you'll see that the 6, 7, 8 derivative is 0. It's always 0. See that 6 derivative is 0, and moreover, for any n greater than or equal to 6, we get this one is always 0. Okay, so you'll see that we do not stop at the first derivative, but we can consider the second, third, fourth, fifth, and even the n derivative. Okay, and okay, this will be very useful, especially in the discussion about the Taylor series or the Maclaurin series in the next semester. So in this case, okay, so you'll see that the derivative of the polynomials here is always polynomials, and in particular, up to some derivative, the derivative will be 0. Okay? And in this case, the 6th derivative and the 7th, the 8th derivative will be 0, and so forth. In general, for the n derivative, when n is greater than 6, these polynomials, the derivative of this polynomial is 0. Okay. Okay, so let us now, this is the polynomial. So let us now take a look at the derivative of another function. Let's say we consider the derivative of fx equals to, let's say, sine of x. Okay. So what is the first derivative of sine of x? Cosine of x. of course, the second derivative will be minus sine of x. And the third derivative is minus the derivative of sine x is cosine of x, so minus cosine of x. And the fourth derivative is the derivative of cosine x is minus sine x, so minus of minus sine x is sine x. So you'll see that here we can calculate the first, the second, the third, and the fourth. And the fourth derivative is actually go back to the function itself. Okay, the derivative, if we start with sine x, the fourth derivative is sine x. Of course, the fifth derivative can be repeated. Okay, here, of course, it is cosine of x. Go back to the first derivative. And the sixth derivative is minus sine x. Then the seventh derivative, go back to minus cosine of x. And the eighth derivative is the function itself. So you'll see that it's periodic in terms of the number of the derivative. So the first start with the function, the first, the second, the third, and the fourth go back to the function. The fifth is the same as the first derivative. The sixth derivative is the same as the second derivative. The seventh derivative is the same as the third derivative. So forth. Okay. And this is similar to the derivative of, let's say, cosine of x. Okay. This is similar to the derivative of cosine of x. So you'll see that if I start with g of x equals to cosine of x, then the first derivative is minus sine x. And then the second derivative is minus cosine x. The third derivative is sine x, because it's a minus of minus sine x. And the fourth derivative here you see is cosine of x. So the same as the function itself. And then the fifth will be the same with the first derivative. The sixth will be the same as the second derivative. The seventh derivative same with the third derivative. We repeat this way. Okay, so you'll see that we discussed with the derivative, the higher order derivative for a polynomial, and trigonometric function, in particular sine and cosine function. Okay, so that's the example of higher order derivatives. And actually, the interpretation of the higher order derivatives is as follows. So, for example, in physics, you learn that, let's say, xt is the position, let's say the position of the moving particle, Okay, so the particle is moving, and then at the time t, let's say the position is given by the formula x of t here. And then the velocity of the moving particle, v of t, is actually the derivative of the position. Okay, the first derivative of the position. And then, so this here is the velocity. Okay, and then the acceleration a of t is actually the second derivative, or the derivative of velocity, or we can see this as the second derivative. So here is the acceleration. Okay. Okay. Of course, as a function, we can actually take the derivative once more, but for the moving particle here, at least we have the interpretation as the first derivative is velocity, and then the second derivative is the acceleration. And of course, if you continue to study the curve, for example, but it's not included in this calculus course, you can actually calculate the curvature of a curve in three-dimensional space, and it will involve the term of third derivative. Okay, so that's one of the interpretation of or the torsion of the curve in the space. Then it will require us to calculate the third derivative. All right. Any question or comment so far? Is it clear up to this point? Okay. So if it's clear, then in the last 10 minutes, I will give the short introduction about the differential and linear approximation. Okay. So this, yeah, I will skip the related rates for the next lecture. Differentials and linear approximation. Okay. So the idea is that for the differential and linear approximation, for example, it's a simple case. For example, if you want to, let's say, approximate the value of square root of 10, for example, what is the approximate value of the square root of 10, for example? If you want to, let's say, calculate the square root of 10 without calculator, for example, you want to approximate its value without even calculating it. So the idea is that something like this, or if you want to, let's say, approximate what is the value of sine, the approximate value of sine 0.1, for example. What is the approximate value? Or cosine 0.1, what is the approximate value? Okay, so that's the idea. So here we want to use simply just the equation of the tangent line. The idea simply is just the equation of the tangent line. For example, if you want to consider, let's say, square root of 10 there. Okay. Okay. For example, if you want to approximate square root of 10, okay, I will draw the graph of square root of x here. Okay, and then we want to approximate what is this value of square root of 10 here. So this is the graph of square root of x. So here y equals to square root of x. Then we want to know what is the value here, square root of 10. Okay. Okay. So the idea is that, okay, near to the square root of 10 here, of course, I can obtain the value of square root of 9 exactly. Square root of 9 is 3, right? So the idea is that we want to approximate it by considering the tangent line, okay, tangent line to the point 9,3, and then we use the value here as the approximation of square root of 10. Okay, I will zoom this. Okay, I will zoom the okay, first clear first, and then I want to use the value here and then drawing the tangent line. So you'll see that square root of 10 is approximately the value of the equation of the line here at x equals to 10 here. Okay. So the idea is just simply finding the equation of the tangent line close to the point x equals to 10, right? Namely x equals to 9. Okay, so that's the idea. So in this case, okay, I will go back to the okay, I will go back here. Okay, so I'll start with y equals to square root of x here, and then I want to know the equation of the tangent line to this curve. Okay, so the equation of the tangent line to the curve y equals to square root of x, at the point when x equals to 9, y equals to 3, so 9, 3. So the idea is that, of course, we should calculate the gradient of the tangent line. Okay, so the gradient of the tangent line is, let's say, m, namely the value of dy dx evaluated at x equals to 9, and of course this corresponds to y equals to 3, right? Okay, so now we want to find what is the derivative of square root of x. Okay, if y equals to square root of x, then it's a derivative dy dx equals to half x to the power minus half, namely 1 over the square root of x. Okay, and if we calculate it at x equals to 9, so the gradient m is the value of the derivative at x equals to 9, and in this case we have 1 over 2 square root of 9, and this will be 1 over 6, right? Okay, that will be 1 over 6. So the gradient is 1 over 6. Of course, if the gradient is 1 over 6 and the line pass through the point 9, 3, then we can obtain the equation of the line. More precisely, the equation of the tangent line is y minus 3 equals to 1 over 6 is the gradient multiplied by x minus 9. So that will be y equals to x minus 9 over 6 plus 3. So if we go back to the previous problem, so the square root of 10 is approximately, here I have to remind you, this is not the equal sign, this is the approximation sign. It's approximately the value of y at x equals to 10 here. So here 10 minus 9 over 6 plus 3. So 3, 1 over 6. So that's the approximate value of square root of 10. And it makes sense because square root of 9 is 3. So at least square root of 10 should be greater than 3. So precisely it's around 3, 1 over 6. Okay? Is it clear? Any question or comment? So that's the idea of the linear approximation. For example, you may repeat the following argument. For example, you consider y equals to sine x, and then calculate the derivative at 0, and then calculate the equation of the tangent line, evaluate at 0.1. The same applies for cosine as well. And yeah, so the general idea is that if you are given, let's say, oops, I missed the, where is the, yeah, this is last one. So the general idea, if you want to find f of x, if you are given f of x, let's say at a certain point, then you want to approximate the value of f at x0 plus delta x, for example. Okay, what is the approximate value? So the approximation will be, suppose that you may calculate f at x0 easily. For example, in the previous example, fx equals to square root of x and x0 equals to 9. So you can calculate square root of 9 easily. Then, for example, you may calculate fx0 easily. Then the approximation will be fx0 plus delta x is approximately f at x0, and we have to add f prime of x0 multiplied by delta x. So that's the idea. And okay, so delta x here is called differential of x and then if we write the difference between these two, okay, and if we write delta y, as f at x0 plus delta x, or delta x or dx. Okay, I will write it as dx or delta x as a differential of x, and fx0 plus delta x minus fx0. But delta y is not the differential of y. dy differential of y is f prime at 0 dx, or f prime at 0 delta x. So to summarize this, delta y is approximately differential of y. Okay. So here, okay, so I will write this as a differential of y. And for example, if you have y equals to f prime of f of x, then dy is simply f prime x dx. Here dx equals to delta x. So okay, so we have to distinguish delta y is the actual value of the difference between the value of f, and dy is the approximate value of that difference. Okay, so dy is actually this term, is the approximate value, and delta y is the exact value. So in the previous case, for example, let's say f of x equals to square root of x. Okay, so delta y is square root of x plus delta x minus square root of x, and dy differential of y is f prime of x dx, namely 1/2 square root of x delta x. So you'll see that they are different, but delta y, the first one, can be approximated by the second one. That's the idea. They are not the same, but the first one can be approximated by the second one. So that's the idea of the differential and linear approximation. All right, probably that's all for the material for today. We'll continue in the next lecture about the related traits, as well as the following topics about the differential and linear approximation. And where is the? I will save it and then stop the recording.